the subject which covers the highest percentage weight in GET chemical engineering is mass transfer. So in this video of Gyanve Science and Engineering, we are going to see the video solutions of subject mass transfer. The first question from mass transfer is, two PEG towers are designed for the mass velocity of the gas. The first has liquid and gas flow rates of 30 kg per second and 1.2 kg per second respectively, while the corresponding flow rates in the second tower are 67.5 kg per second and 1.8 kg per second. The ratio of the design diameter of the wider tower to the narrow tower is. So this is basically the question of PEG bed tower design. So here we are considering two cases. Case 1, where the vapor flow rate is given 1.2 kg per second and the liquid flow rate is given as 30 kg per second. And case 2, where vapor flow rate is given as 1.8 kg per second and liquid flow rate is given as 67.5 kg per second. Here we are using some technical terms of designing part, that is K4, that correspond to the generalized correlation factor, FP, that is the packing factor for the PEG tower packing material, VM, that is the gas flow rate per unit area, and of course the vapor density and liquid density of the fluids. So here we know the relation between K4 and VM is, K4 is given as 13.1 into VM square into mu of L divided by rho L raised to power 0.1 whole divided by rho V into rho L minus rho V. This is the empirical relation where mu L is the viscosity of liquid, rho L is the density of liquid, and rho V is the density of vapor. So here we are considering the assumptions that these parameters are not varying in the PEG tower. So we are considering that K4 is proportional to VM square. Now also K4 also depends on some other parameters like liquid flow rate per unit area and vapor flow rate per unit area with the flow value. And the relation that is given is flow value equals to liquid flow rate to the ratio of liquid flow rate to the vapor flow rate root of liquid flow rate to vapor flow rate. So now we can see the flow value depends on the ratio of liquid flow rate to vapor flow rate, and also there is a relation between flow value and K4. And the curve defines the pressure drop here, where this curve defines the pressure drop of 4 mm of Hg, 4 mm of H2O, where this defines the 8 mm of H2O, and this is the final pressure drop that corresponds to the flooding velocity. So here, as we know, the K4 also depends on FLV, and FLV depends on the ratio of liquid to vapor flow rate. But here we are considering with the assumption that the K4 is not changing in FLV. So the FLV will change such that the pressure drop will counterpart the change. So as we increase the FLV, the value of pressure drop will increase such that the value of K4, that is generalized correlation factor, that will remains constant. And from all this we can deduce that the K4 is proportional to VM square. So here we have K4 proportional to VM square. That can be written as V upon A1 square equals to V2 upon A2 square. This, as we have been provided with V1 and V2 for case 1 and case 2. So we are putting the values as V1 as 1.2 divided by area is given as pi by 4 d1 square equals to 1.8 divided by pi by 4 d2 square whole square. And from here, solving we will get the ratio d1 to d2 as 1.8 divided by 1.2 to the root, and that comes out to 1.225. So the ratio of wider diameter column to the narrow diameter column will be 1.225 in this case. Now moving to the next question. The next question is, according to the surface renewal theory, the unit of fractional rate of surface renewal is. So this is basically the question related to dimensions. So here we know from surface renewal theory, mass transfer coefficient is proportional to under root of diffusivity, where the unit of K is in meter per second, that is equal to the diffusivity, which unit is meter square per second. So from here we can solve as that will come out to second inverse. So this is basically the unit of fractional unit of surface renewal. So the next question is, for absorption of H2S from a mixture with hydrocarbon vapor into an aqueous alkylamine solution, the liquid phase mass transfer resistance is. The options are given: significant higher than that of the gas phase, negligible compared to that of gas phase, equal to that of gas phase, and dependent on the gas phase mass transfer resistance. So here we have one stream that contains H2S and hydrocarbon, which will absorb liquid that contains alkylamine. So here we have gas phase, we have gas and liquid interface, and liquid phase. Now, as we know that the substance like H2SCO2 has more affinity towards alkylamine, the absorption of these compounds in alkylamine is more. So, the resistance offered by liquid will be less as compared to the gas phase. So, here we can conclude that the B option, that the mass transfer resistance will be negligible as compared to that of gas phase in liquid phase. The next question is, it is decided to extract A from a feed containing 20 mole % A and 80 mole % B in two ideal cross current stages as shown in figure. So here we have been given two stages, stage 1 and stage 2. We have feed containing A and B and a solvent C to extract the A. Here also, as it is given that the moles of C used in both stages are same. So here also we are taking solvent used is C and the outstream. Now it is given that the B and C are immiscible liquid. So what we can conclude here is that the raffinate phase will contain A and B, whereas the extract phase will contain A and C. And stage 2, extract phase will contain A and C, whereas the raffinate phase will contain AF, AR and B. Now here what we have been given is, in stage 2 60% of extraction is taking place. So if we assume 100 moles in feed A plus B, then A will be 20 and B will be 80, as it is given as 20 mole % of A is present in feed. So A will be 20 moles and B will be 80 moles, and 60% of A is extracted. So the extract phase will contain 60% of 20 moles, that will come to 12 moles, and remaining A will present in raffinate phase, that is 8 moles. So from here we have A, B in feed, A in extract phase, A in raffinate phase, and we need to calculate, and B is same 80 moles. We need to calculate how much C is used in stage 1. So using the equilibrium relation, we have 1.5 times of X star, where Y is moles of A divided by moles of C in extract phase is equal to 1.5 times of moles of A upon moles of B in refined phase. So using this, we have moles of A in extract phase is upon moles of C we need to find equals to 1.5 times of moles of A in refined phase is 8 moles and moles of B in refined phase is 80 moles. So from here C comes out to 80 moles. So the same amount of C is used in stage 2, so C will be 80 moles. Now here we don't know the value of AE and AR. So in this stage 2 we are applying, first is the equation is mass balance. So the mass balance of component A will be equals to moles present in refined and moles present in extract phase will be equal to total moles in feed of stage 2, that is 8 moles. So we have one equation, AE plus AR equals to 8. Now the second equation we will generate from equilibrium relation, that is Y star equals to 1.5 times of X star. Now Y is moles of A in extract phase, that is AE, upon moles of C in extract phase, that is that we have calculated 80 moles, will be equals to 1.5 times of moles of A in refined phase, that is AR, divided by moles of B in refined phase, that will be equals to B, because B and C are immiscible liquids. So it will be 80. Hence we got A equals to 1.5 times of AR. So this is the second equation we have obtained. Now solving equation 1 and equation 2, we get AR equals to 3.2 moles. By substituting value of AE from this to equation 1, we can get the value of moles of A in definite phase, and that comes out to 3.2 moles. Now what we have been asked is the percentage mole in definite phase after stage 2. That will be equals to moles present in refined phase, that is 3.2 times upon total moles present in refined phase, that will be equals to 3.2 plus moles of B, that is equals to 80 moles. So solving this, we will get the mole percent of A will be 3.84%. So the percentage of A present in refined phase after extraction of stage 2 will be 3.84%. So this is the answer. Now the next question is, the binary distillation column is designed by a McCabe-Thiele method to get a distillate mole fraction of 0.9. The enriching section operating line has intercept with y-axis at 0.3 mole fraction. The ratio of liquid to vapor molar flow rate in the enriching section is. So here we have one distillation column with feed and the vapor flow rate is V. We have distillate. This is the liquid flow rate used as a reflux after condensation, and this is the bottom stream reflux and outlet. Now here we have been asked the ratio of liquid to vapor. So first, from enriching section operating line, we can which is given as y equals to x r upon r plus 1 x plus xd upon r plus 1, where r is reflux ratio and xd is the mole fraction of distillate in product. So here we have been given that the intercept of this equation is 0.3. That is xd upon r plus 1 equals to 0.3. xd is given as 0.9. So using this, we can get the value of r as 2. Now what is r? R is written as L by D. This is L by D. Now L by V. What is V? V is the total vapor flow rate that is taken out from the top of the column, which is equals to L plus D from mass balance. We have V equals to L plus D. Substituting in this, we have L upon V is L plus D, which is 1 upon 1 plus D by L. So we have L by D as 2. So D by L will be half. So substituting this, we will get 1 upon 1 plus 1 by 2. That will come out to approximately 0.66. So the ratio of liquid to vapor in the enriching section from the top of the column is 0.666. So moving to the next question. A fiberboard sheet of given dimension is being dried by suspending it horizontally in a current of hot dry air. The edges are insulated so that drying takes place only from the top and bottom surfaces. The wet sheet weighing 16 kg with initial moisture content of 60% loses moisture at a constant rate of 1.25 into 10 to the power minus 5 kg per meter square seconds until the moisture content falls to 30%. So all moisture contents are on dry basis. The time required for drying during constant rate period is asked. So in this question, we have been provided a fiber board of dimensions 1.5 meter breadth and 2 meters in length with thickness as 15 mm. And from the top and bottom, the air is passed for drying. As we know that the equation for rate of drying is given as ms divided by a integral of dy by n. Now, as in the question it is given that the rate of drying is constant. So this equation can be reduced to T equals to m divided by a to delta y by n. So what we have been given is mass of solid on dry basis is 16 kg. So first we need to convert this wet basis into dry basis. That is given as mass of solid on dry basis equals to mass of solid on wet basis multiplied by 1 minus xi, where xi is the initial moisture content on wet basis. So now as we know the relation for conversion of dry basis to wet basis is S equals to capital Xi upon 1 minus Xi. Now we have been given capital S, that is the initial moisture content on dry basis. So from here using this relation we can calculate the value of initial moisture content on wet basis. That will be equal small xi equals to capital X divided by 1 plus capital Xi, and capital Xi is given as 0.6. So that will be 0.6 divided by 1 plus 0.6. That comes out to 0.375. Now this is the initial Xi. So the mass of solid on dry basis will be 16 into 1 minus 0.375. That comes out to be 10. So using the relation this, we have calculated ms. Now the area has been provided, that is 1.5 into 2, but in this case we are drying the fiber board from two sides, so the area will be the twice. So substituting the values, we will get T equals to 10 divided by area, that is 1.5 into 2 into 2 into rate of drying, that is given as 1.25 into 10 to the power minus 5 kg per meter square second into delta y. Delta y is given the initial moisture content minus final moisture content on dry basis. So calculating this, we will get T equals to 64,000 seconds. That we need to convert into hours. That will be divided by 3600. That will come out around 11.11 hours. So the answer for this question is 11 hours per drying. So the next question is, an azeotropic mixture of ethanol and water is to be separated in a distillation column using benzene as an entrainer. At the column operating conditions, two liquid phases are formed on a tray. The degree of freedom of the system of the choice of intensive property of equilibrium is. So here we have been given a system that contains ethanol and water. Now, as we know that the ethanol and water forms an azeotrope, so the benzene is used as an entrainer to separate this mixture as from ethanol to water. So we have, after adding benzene as an entrainer, two phases will form. That will contain, the first phase will contain ethanol and benzene, whereas the phase 2 will contain water and benzene. Now here we have been given that we have to find the number of degree of freedom in this type of system. So we using the most general relation for degree of freedom is NF equals to C minus P plus 2 minus R minus S, where the C corresponds to the number of components present in the system, P corresponds to the number of phases, R corresponds to the number of independent reactions that taking place in the system, and S is the special constant that is generated here due to the azeotropic mixture. So we have C, number of components are 3, as we can see, ethanol, benzene and water. So 3 minus number of phases are given as liquid and vapor, as both can be present in these forms. So we have 2 plus 2 minus R, as there is no reaction taking place in this system, so we are considering R as 0, and minus S. S is the special constant which value is 1 just because of azeotropic formation of ethanol and water system. So from here what we will get the number of degree of freedom as 2. So in this system we have the number of degree of freedom as 2. That's all from Master Answer part. For more such informative videos, stay tuned with Gyanve Science and Engineering.